Welcome to the NORA Gold Hydronics online class. Hydronics is the science of heating structures using water as the heat transfer medium. Water is heated in the boiler, then travels through a network of pipes throughout the building, and then to a heat emitter which uses the heated water to heat the home. This is a typical hydronic heating system with an indirect water heater. The next several slides will examine some of the major components of the system. Starting with the boiler, it's important to understand the information on the nameplate. For example, the firing rate is the gallons per hour that the boiler is rated for. This boiler is rated at 0.75 gallons per hour and should be fired with a 0.75 nozzle with 100 psi pump pressure. If the pump pressure is higher, the nozzle must be downsized. The DOE capacity is a U.S. Department of Energy rating of the BTUs when fired at a specific gallon per hour input. The net rate is used to select a properly sized boiler based on a heat loss calculation. It includes a 15% allowance for piping and pickup losses. The pressure relief valve protects the boiler from overpressurization. Relief valves on most residential systems are set to open at 30 psi, but may release and weep around 27 psi. The relief valve must meet or exceed the boiler DOE rating. The low water cutoff protects the boiler against damage in a low water situation. The low water cutoff is installed at or above the boiler's safe water level. If the boiler water drops below that level, the control opens a circuit to shut off the burner. Air elimination devices are used to control air bubbles in the heating system. There are two main types. First, we'll look at air scoops. As water enters the scoop, its velocity slows down, causing air bubbles to separate and rise into the upper chamber where they pass out of the system through an air vent. Air scoops will not function properly unless there is a minimum of 18 inches of straight pipe on the inlet side. The second type is air separators. These devices offer enhanced air separation and do not require a run of straight pipe to the inlet side. They should be placed as close to the boiler as possible. Here you will see an animation, courtesy of Spirotherm, of how an air separator works. Air vents are installed in the system piping to remove air bubbles. There are two types of air vents. The first is automatic air vents, and these have a float which opens a spring-loaded venting valve to purge air from the system. When using automatic air vents, the system pressure at all vent locations should always be at least 3 psi above atmospheric pressure. This prevents air from being pulled into the system. And then manual air vents are normally installed on individual heat emitters and are used to remove air during system startup and when troubleshooting air problems in a system. Now let's take a look at pressure-reducing valves. Pressure-reducing valves serve two functions. They lower street pressure to what's required for the heating system, and they fill the system with enough water to ensure the water at the top is under enough pressure to vent air while allowing the water to circulate. Most residential pressure-reducing valves are set at 12 psi, which is enough for a typical two-story house. Let's take a look at why 12 psi is appropriate for a typical residential application. First, let's remember that 1 psi will lift water 2.31 feet. Therefore, 1 psi is equal to 2.31 feet of head. Now, in this application, we're going to have to lift the water 18 feet, which is the distance from the pressure-reducing valve to the top of the heat emitter on the second floor. Just under 8 psi will actually lift the water to the top of the system, but will not be enough pressure to allow the water to circulate. So, 3 to 4 psi needed to be added to ensure positive pressure at the system's highest point. The pressure reducing valve, in this case, should be set to 12 psi. Backflow preventers. Backflow preventers are installed on boiler feed lines to prevent contaminants in the system water from affecting the potable water supply. Backflow preventers are installed on boiler feed lines to prevent contaminants in the system water from affecting the potable water supply. Expansion tanks. Expansion tanks are needed because the water in a closed heating system expands up to 5% when it's heated. Expansion tanks give the expanded water a place to go and provide a way for it to return to the system as it cools. Without expansion tanks, system pressure would rise and the relief valve would discharge almost every time the burner cycled. Diaphragm tanks have an internal rubber diaphragm that separates the system water from compressed air. Before being installed on the system, the diaphragm is fully expanded and flush with the inside wall of the tank at the system tapping. Once the tank is installed, the system water pushes against the diaphragm. As the system heats up, the expanded water forces its way into the tank. As the water cools, the air pressure forces it back out of the tank. The air side of the tank should be charged to the system operating pressure. If the system is set to provide 17 psi, the air side of the tank should be pumped up before being installed to 17 psi. If the air pressure doesn't match the water pressure, the relief valve may discharge. Under normal operation, steel compression tanks are typically about 2/3 full of water and 1/3 full of air. As the water heats up, it pushes up against the top of the tank, compressing it. As the water cools down in the off cycle, it condenses and the air expands back into the original volume. Next, we will look at a circulator. A circulator's job is to take water from the boiler and move it through the installed radiation and return it to the boiler. It does this by creating a pressure differential. It takes water in at a given pressure and then sends it out at a higher pressure. When a circulator is in operation, water flows into the suction side of the volute, which is wider and larger than the discharge side, and then into the eye of an impeller. As the impeller rotates, the vanes slap the water from the inside to the outside of the impeller, adding velocity. The water then moves to the discharge side of the volute, which is smaller and narrower. The collection chamber on the discharge side turns the energy due to velocity into pressure. Thus, water enters the circulator at a certain pressure and leaves at a higher pressure. The thickness, diameter, and construction of impellers all play a role in the performance of the circulator. The thickness determines its flow capacity. The thicker impellers produce more flow. The diameter determines the velocity the circulator can impart. The larger the diameter, the more velocity the circulator can impart, and the more pressure it can produce. Zones. A zone is an area of a building controlled by a dedicated thermostat. A common residential zoning system has one zone for the first floor and another for the second floor. This system requires either 2 thermostats, 2 flow valves, and 2 circulators, or 2 thermostats, 2 zone valves, and 1 circulator. Zone valves are thermostatically operated 2-position valves. Zone valves are normally closed and only open when there is a call for heat from the thermostat they're wired to. Once the valve is fully open, the circulator is powered, allowing water to flow through that zone. 1 thermostat and valve is required per heating zone. When zone valves are not used, flow control valves are installed in the supply piping to prevent gravity circulation when the thermostat is not calling for heat. Flow valves open, allowing water to move through the system when the circulator operates, and they close when the circulator stops running. Indirect water heaters. Indirect water heaters are storage tanks with internal heat exchangers. They are equipped with an aquastat that controls a circulator to move hot boiler water through the inside of the heat exchanger, heating the domestic hot water in the tank. Thermal expansion tanks. Domestic water expands when it's heated, and 50 gallons of cold water becomes 52 gallons of hot water. Thermal expansion tanks will take up the excess water, preventing continual discharges from the relief valve. Temperature and pressure relief valves. Temperature and pressure relief valves protect the system against excessive pressures and temperature. Typically, they open at 210 degrees Fahrenheit and/or 150 psi. Heat emitters. Heat emitters receive heat from the hot water circulating through the piping and warm the air around them. The heated air expands and rises, displacing cooler air which falls, creating heat convection currents. Fin-tubed and cast iron baseboard use convection to distribute heat. Baseboard heating is usually located along outside walls to help the convective currents and to remove the feeling of a cold wall or window. Finned tube baseboard typically features copper tubing with aluminum fins attached. It heats up rapidly and dissipates its heat quickly. Clearance in front and proper space under the cabinet are critical for proper operation. Cast iron baseboards heat up slowly and cool off slowly. Surface temperatures are high and there are no protective enclosures. Cast iron baseboards also provide radiant heat because the large mass of iron stays hot after the circulator shuts off and slowly releases energy into the space. Convectors are similar to fin tube baseboard, but they tend to be thicker, higher, and not as long. They heat up quickly and cool off quickly. Surface temperatures are not an issue as they are protected with covers, and like fin tube baseboard, they need enough room in front to create convective currents. Cast iron radiators deliver heat in a way that is similar to cast iron baseboard. They are relatively large and have a higher water content than baseboard. Flat panel radiators are a cross between fin tube baseboard and radiators. Their steel mass adds to the radiant energy in the room. Fan coils are small convectors with fins installed in the ductwork. Hot water circulates through the coils, and air is circulated in the home by the unit's fan blowing across the fins. Radiant heating systems deliver heat by radiant heat transfer. A typical radiant system heats the floor anywhere from 75 to 85 degrees Fahrenheit. Depending on the installation method, the water temperature needed for heating can be as low as 100 degrees Fahrenheit. In a radiant system, the boiler typically operates at around 180 degrees Fahrenheit, while the radiant system operates at a lower temperature, thus creating the need for a mixing device. Mixing devices blend return water from the radiant panel with boiler water before sending it through the radiant panel system. When a mixing device is used, there must be a circulator after the mixing device to ensure flow through the radiant panel.